Hello, my name is Luis Serrano and this is Serrano Academy, and in this video I am going to tell you about Stable Diffusion and how it's used to generate some amazing images. So you've probably seen and played with some of the state-of-the-art image generators like Midjourney, Dream Studio, Firefly, DALL-E, and others. In these, you add a prompt as imaginative as you want, and the model gives you a pretty faithful image described by your prompt. I have been amazed by these models and I play with them a lot. For example, here is a prompt that I added recently. I said a penguin captaining a pirate ship in a storm in the Caribbean. The sunset can be seen in the background behind the clouds. And the model drew this, which is pretty accurate. So now I'm asking myself the question, how is it that these models work? And how is it that they can draw such amazing images? In particular, images that are definitely not in the data set that they were trained on. Because the dataset may have pictures of penguins and pirates and sunsets, but the model manages to understand the sentence I gave it and then combine the right images to form the output. That is fascinating. Now, for these models to work, you need a lot of data and a lot of parameters. However, at the end of the day, the architecture consists of 3 neural networks that process the text, output an image, and then clean the image. So let me show you how all this works. So as I mentioned, Stable Diffusion uses 3 neural networks. The first one is the one that turns the text into numbers. So here I have the prompt about the penguin on the pirate ship in a sunset. That is turned into a list of numbers called a vector. It can be a really long list of numbers. There could be hundreds or thousands of numbers, but it's a pretty good description of them. And this is called an embedding. I will tell you more about those in a minute. The second neural network is the one that takes these numbers and turns them into an image. So the numbers that come out of the first neural network that are the interpretation of the text is now turned into an image. Now this image can be pretty rough. So we use the third neural network to refine the image. It takes a rough image and turns it into a nice crisp image of the stuff that the text is describing. So in this video, I'm going to tell you about this process, the one that turns text into numbers and then numbers into a rough image and then the rough image into a crisp image. And then after the high-level explanation, we're going to have an example. In the example, we have a very small data set of words that are going to be turned into some very simple images. And the way we're going to do it is with some very small neural networks. So you'll be able to see how it works in detail in a very simple example. So let's start with the first neural network, and that one has to do a lot with embeddings. So if you've seen any of my previous videos, you know embeddings are a big deal because I always start by talking about embeddings. Embeddings are really where the rubber meets the road, because it's when you take the stuff that's visible for humans and turn it into something visible for computers. Things that are visible for humans are video, images, text, sounds, etc. And for computers, they only talk in numbers. So anything that turns an image or text or anything into numbers is an embedding. And it's really the first part of each big model because you got to turn things into numbers in order for the computer to work with them. So the first thing we're going to see is a word embedding. I like to see words embeddings as ways to locate words in, for example, a plane. So if I'm going to throw words in this plane, let's say I have the words apple, pear, and watermelon over here, and then the words car, bicycle, and truck over here, and then the words dog and cat over here. So what's a peculiarity of this embedding? Well, that similar words get located close by. For example, an apple is close to a pear because they're similar, and a car is close to a truck because they're similar, and the same for dog and cat. That is one of the main properties of an embedding. Now remember that I said an embedding is a way to turn words into numbers. Where are the numbers? Well, they are in the horizontal and vertical coordinate of the plane. So for example, over here, apple gets sent to 5, 7, dog gets sent to 4, 1, cat gets sent to 5, 1, and so on, because you have to take, for example, from the origin to get the cat, you have to make 5 steps to the right and 1 step to the top. And so this pairing is an embedding. Now I'm not going to have it as a list of numbers for each word. I'm actually going to have it encoded as a neural network. So a neural network takes every word and processes it and turns it into a bunch of numbers. Now it doesn't have to be 2 numbers. It could be 3, it could be hundreds, it could be thousands. And those numbers are a pretty good description of the word. But for now, let's think of it as 2 so that we can see them visually in the plane. So the first of our neural networks in Stable Diffusion is going to be this neural network over here. It's going to be called an embedding neural network. And it's the one that takes words and turns them into numbers. How do these get built? Well, it's a very complicated process, and if you'd like to learn more, check out this video on my channel called What are Transformer Models and How Do They Work? In that video, I talk about word-to-vec, which is a pretty useful way to build embeddings. Now, we have word embeddings, but we also have image embeddings. And an image embedding is very similar. It's actually a way to locate images in the plane. So here I have the image of an apple, a pear, a watermelon. Here I have the images of a car, a bicycle, and a truck. And over here I have the images of a dog and a cat. So again, every image gets associated with the two coordinates in the plane. And in real life, this would be hundreds or thousands of coordinates, but I'm going to see them as two. And so what do we have? Well, on the left, we have word embeddings, and on the right, we have image embeddings. And the idea is to find a way to turn the left embedding with words into the right embedding with images. That's a way you would be able to take words and turn them into images. So in this example, it's pretty easy. All we have to do is send the words to their corresponding images, which due to a strike of luck are actually located in the exact same position as the word. Now, of course, this is not what's going to happen in general. If we build a text embedding and we build an image embedding, they have no reason to locate the words and the images in these exact same places. As a matter of fact, they could have completely different dimensions. The text embedding could have hundreds of coordinates and the image embedding could have thousands of coordinates, and they have nothing to do with each other. So what we want is to find a map, so a way to associate the words in the left with their corresponding images on the right. We need to find a rule that takes a word on the left and puts it into its corresponding image in the right. And how do we do it? Well, you guessed it, with a neural network. We're going to take a neural network and we're going to train it to take each word in the left and map it to its corresponding image on the right. So for example, the dog goes here, the cat goes here, etc., etc. And of course, neural networks have numbers as the input, which are the coordinates over here, and numbers as the output, which are the coordinates over here. So all we have to do is take a huge table of coordinates of words in a text embedding on the left and map them to the coordinates of the corresponding images in the right. In other words, we train a neural network with the input being the coordinates of the words and the output being the coordinates of the corresponding images. As I mentioned, we don't have to have two coordinates. We could have many on the left and many on the right, and they don't even need to be the same number. But the idea is that we're going to train a neural network to map coordinates of words into coordinates of images. Now, the picture is a little more complicated, but not very much, because in reality, text embeddings are a lot more powerful than just for words. They can actually take entire sentences or longer pieces of text and map them into coordinates. So for example, I can have a few sentences over here that talk about science, a few sentences over here that are titles of Beatles songs, and a few sentences over here that are greetings. And just like in the word embeddings, similar sentences are going to be located in similar places. And image embeddings can also be much more complicated. I don't need to have an apple or an orange. I can have much more complicated images that are not described by a single word, but actually described by an entire sentence or even more. And the idea is that I take a text embedding of longer pieces of text and I can send it to an image embedding of more complicated embeddings. For example, this one has 4 images: a ship in the sea, an airplane in the sky, which are close to each other, a dog and a cat, and people in a park. And of course, you can imagine an entire paragraph description of a very complicated image. These ones would belong here. And the idea again is that we're not going to be that lucky to have the images match up the texts like here. In reality, the image embedding and the text embedding could be very different. And what we need to do is train a neural network to match every single paragraph in the dataset with its corresponding image in the image dataset. And if this neural network gets well trained, then it's going to be able to take a new sentence that has never seen before, for example, a penguin dressed like a clown, and be able to draw an actual penguin dressed like a clown. This is the image I got when I put a penguin dressed like a clown in a Stable Diffusion model. And the power of this is that text embeddings actually understand what's being said beyond the words. It actually understands the semantics of the sentence. So I like to imagine it like this. Let's say that a neural network knows how to draw a clown because there's a clown in the dataset, and it also knows how to draw a penguin because there's a penguin in the dataset. Now, when you say a penguin dressed like a clown, maybe it's never seen it. But that's okay, because I can somehow interpolate between the clown and the penguin. So if the neural network knows how to get the sentence a clown into the image of a clown, and it also knows how to turn the sentence a penguin into the image of a penguin that's over here, then a penguin dressed like a clown is going to be somewhere in the middle, so the neural network is going to send it somewhere in the middle, and it's going to get a penguin dressed like a clown. Obviously, I have vastly oversimplified this. There's a lot more coordinates, and these neural networks can be very complicated, but that's more or less the idea. That once you have embeddings where you turn sentences and images into numbers, then the arithmetic that happens between the numbers also turns into arithmetic that happens between the sentences and between the images. So it's not too far-fetched to think of a penguin dressed like a clown as the midpoint between a penguin and a clown in both the text and the image embedding. Funny enough, I tried to draw a clown dressed like a penguin, and the model gave me the exact same thing, a penguin dressed like a clown. So in some way, these models are still kind of limited. The model, when it sees penguin and clown, it still imagines a penguin dressed like a clown, because that's just a little more imaginable than a clown dressed like a penguin. Obviously, these models are always improving, and soon it's going to be able to draw a clown dressed like a penguin, and maybe some models are able to draw it. But I just want to point out to you that these models, although they're amazing, they still have some visible limitations. And I encourage you to play with these models and make them draw crazy things and see what they can do and what they can't. So far, we've seen two neural networks, right? The first one is the embedding, and the second one is the image generator. So the embedding is the one that takes the sentences and turns them into vectors or into lists of many numbers. Here I have 4 numbers represented by shades, but in reality it would be hundreds or thousands of numbers. And then we have the image generator, which is the one that takes these vectors, these lists of numbers, and turns them into images. And so one would think that that's it, right? Take the sentences, turn them to numbers, take the numbers, turn them into images. But in reality, we need one more step. Why? Well, because in real life, these images that come out are not so nice. They're actually pretty rough. And it's understandable, because images can be pretty complex. And when we're sending a sentence into an image, well, maybe the computer needs a little help. Maybe the computer can figure out that it's drawing a dog here and a cat here, but it's not able to do it so well. So what do? Well, we give it a booster. So what we do is we have a third neural network called the diffusion model. And that one takes rough images and turns them into crisp, neat images. And as I said, that's another neural network. So that is the third one. Now let me tell you a bit more about this diffusion model. So let me tell you a bit more about the diffusion model, which is the one that makes the image sharp. The diffusion model is a neural network that takes all these rough images on the left and turns them into the crisp, sharp images in the right. And how do they work? Well, like a lot of neural networks, what you have to do is feed it the right data for it to learn. And what we're going to do is we're going to take a bunch of images that are crisp, and then we're going to add some noise to them. So adding some random numbers here and there to the pixels will turn them into something a bit noisier. And then we're going to do the same thing again, and again, and again, and again, until we get pretty much full noise. And then we are going to train a neural network to go in the other direction. So it's going to take each one of the noisy images as input and return the previous one in the chain. In other words, the input to the neural network is an image with some noise, and the output is the image with a little bit less noise, which is exactly the previous image before we added the noise. So we add the noise and then we train the neural network to remove it at each step of this process. So the input is going to be a bunch of images and the output a bunch of images with a little bit less noise. That is the diffusion model. And believe it or not, that is the solution. When we apply these diffusion models, and you can apply it many times, you will go from the rough images on the left to the pretty sharp, good-looking images on the right. And that is the big picture of a stable diffusion model. We have the three steps: embedding, image generation, and diffusion model. And the embedding takes text and turns it into vectors, which are long lists of numbers. The image generator takes these lists of numbers and turns them into rough images. And the diffusion model takes these rough images and turns them into sharp, nice images. And each one of these is a big neural network that is trained to do its job. So in high level, this is what we have. But now let me show you an example. Now that you've seen the big picture of a stable diffusion model, let me show you an example. In this example, I have taken a very small set of sentences and a very small set of very simple images. And we're going to build three small neural networks that are going to help us build new images from sentences that don't appear in the dataset. Let's begin. So the setting we're going to have is a city called Batlantis. And in Batlantis, a lot of pretty cool people live, and they have a pastime, which is that they really love to play sports. But they only like sports that have balls and bats. So some of them play baseball, some of them play cricket, and pretty much any sport that has balls and bats. And we're going to create a stable diffusion model for the people in Batlantis. Now, the people of Batlantis have a beta set. And in this beta set, you have a lot of images of balls, could be baseball, could be cricket, could be anything, and a lot of images of bats. Now, it just so happens that all the balls are in the bottom left corner of the images, and all the bats happen to be diagonally located from the top left to the bottom right. That's just how people in Batlantis take pictures. Now, Batlantis has good technology. As you can see, they have AI models, but the technology is a little basic. As a matter of fact, their computers only have 2x2 screens. So they're 2 pixels tall by 2 pixels wide. And they're also monochromatic. So everything is in black and white and different shades of gray. So somehow when we take a picture of a ball or a bat, it has to be displayed on these pretty rudimentary screens. So how do pictures of ball look? Well, they look like a black or dark gray dot in an otherwise clear screen. And the dot is always in the bottom left of the image. And how do bats look? Well, they look like a strong diagonal in an image that is otherwise clear. So we have 2 dark pixels in the top left and bottom right, and the other 2 pixels are white or light gray. And that's our entire dataset. We only have balls and bats. There are absolutely no images of a ball and a bat. So if we wanted an image of a ball and a bat, we wouldn't know what to do. However, we can build a model that's going to be able to draw an image of a ball and a bat. And how would this look? Well, if you put a ball and a bat together, then the diagonal is dark and the bottom left corner is dark and the top right corner is going to be light. So now I'm going to show you how to train 3 neural networks that will be trained with images from balls and bats and will be able to create an image of a ball and a bat together. So let's start with the simplest of these neural networks, which is the text embedding. For a text embedding, let's look at 2 coordinates, the coordinates of ball and the coordinates of bat. And where are the sentences going to live? Well, the sentence ball has 1 time the word ball and 0 times the word bat. So it's going to live in the coordinate 1, 0. The sentence bat has 0 times the word ball and 1 time the word bat. So it's going to live in coordinate 0, 1. And the sentence ball and bat is going to have 1 time the word ball and 1 time the word bat. So it's going to live in the coordinates 1, 1. Now, all we have to do is build an embedding that will send these 3 sentences, ball, bat, and ball and bat, to the corresponding vectors. Now, I'm going to be building small neural networks here, and they're pretty self-explanatory because they're made of vertices and edges. But if you want to know more about them, check out this video on my channel about neural networks. So, to build the neural network, we need 2 inputs and 2 outputs. The 2 inputs are ball and bat, and the 2 outputs are the first coordinate and the second coordinate. And all we need to do is connect the ball with the first coordinate with an edge of weight 1 and connect the bat to the second coordinate with a weight of 1 and then put zeros on the other 2 weights. So what happens here? Well, when we take the word ball, then that's a 1 and a 0 and it gets sent to 1, 0, which is the vector 1, 0. When we take the word bat, that's a 0, 1 and that gets sent from 0, 1 to 0, 1. And finally, when we take ball and bat, that's 1 times ball and 1 times bat, that gets sent to the vector 1, 1. So you may be thinking this is a pretty simple neural network. This is because the example is simple. In reality, embeddings can be very complicated, but I want to show you that even something very simple can be written as a neural network. So now we have the first neural network, the embedding one. Let's go for the more complicated ones. So now that we have the text embedding, let's build the image generator. So we already have the text embedding on the left, and I'm putting the image of the ball and a bat there for reference, but in reality, it's just a text embedding. So the horizontal axis is the word ball and the vertical axis is the word bat. And now let's build a pretty optimistic image embedding on the right. Let's say that we have a horizontal axis which represents the image of a ball and a vertical axis which represents the image of a bat. But remember that these appear in a monochromatic pixelated image of 2 by 2 pixels. So the horizontal axis looks like this. In the origin, you have an empty image, completely white, and as you move to the right, the bottom left corner, which is the one representing the ball, gets darker and darker. And the vertical axis is the image of the bat. So as you go up in this axis, you're drawing a bat, which remember, it's a diagonal. So that diagonal gets darker and darker. So anything that is close to the bottom right looks like a ball. And anything that is close to the top left looks like a bat. And what happens with the top right? Well, those are the images of a ball and a bat. Now, as I said, this is too optimistic. This is not the image embedding we are going to have. The image embedding looks very different. As a matter of fact, the original image embedding you would have has 4 dimensions because our image has 4 pixels and we have 1 dimension per pixel. This axis over here represents the darkness of the top left pixel. This one over here, now I'm going to give them different colors for clarity, represents the top right pixel. And so anything in this plane over here is an image where the top left and the top right pixels are colored in some level of grayness or blueness. Now this is 2 dimensions. If I were to add a 3rd dimension, this one, actually think of it as a 3rd dimension, so it comes out of the page in front of you. The 3rd dimension represents the color of the bottom left pixel that now I'm going to draw as red. So now we have a cube, and anything that's floating around in this cube has colors in all the pixels except for the bottom right and some level of intensity, and the level of intensity tells us where in each of the axes it's located. Now I'm in trouble because I ran out of dimensions. I can't really think in more than 3 dimensions because humans can't see in more than 3 dimensions. So I'm gonna make an attempt to draw the 4th dimension, and you may have to bear with me. This is how I see the 4th dimension. Imagine that I'm taking this space and making many copies of it, let's say infinitely many of them, and I make them along this 4th axis. So imagine this 4th dimension here that represents the color or the intensity of the bottom right pixel, which I'm going to draw in green. And so let's imagine a 4-dimensional world. So 4 axes flying around in 4-dimensional space, and each one represents the intensity of each one of the 4 pixels. So if you were to imagine how the space of images look like, if you were to have a screen of hundreds or thousands of pixels, it would just be a 1000-dimensional world where each of the axes, each of the dimensions, is the intensity of each one of the pixels. Now, of course, a good image embedding will be able to bring that many dimensions down. But let's work with these 2 embeddings. So on the left, we have a 2-dimensional text embedding, and on the right, we have a 4-dimensional image embedding. And we know some information. We know that the word ball has to go here because that's the image of a ball. It's a bottom left pixel with high intensity, and the rest of the image is white. Now, where do you think the word bat would go? I encourage you to actually pause the video and see where the bat would go. And I'll tell you, look at the black and the green axis. These 2 form a plane. And I can draw the plane here. That's easy to draw because it's 2-dimensional. And in this top right corner of the plane lies the image of the perfect bat. So this bat goes over here. Now I need you to help me with your imagination. Where would bat and ball go? Well, let's forget about the blue axis, and now we have a 3-dimensional space. And you can think of this cube over here formed by the black, green, and red axis. And on the opposite corner of this cube lies the bat and the ball. It's here colored in black, white, red, and green. So I hope I've given you a decent idea of how this 4-dimensional image embedding would look like. And now what we need is to find the map between the 2-dimensional text embedding and the 4-dimensional image embedding. And what we have to do is to see where the things that we know go. So as you've seen before, the ball, which has coordinates 1, 0, goes to the red ball in the right that has coordinates 0, 0, 1, 0. And the bat that has coordinates 0, 1 goes to the bat which is colored in black and green and that has coordinates 1, 0, 0, 1. If those 4 coordinates are not clear, they're going to be clear pretty soon, because what I'm doing is reading off the intensity of each pixel from left to right and from top to bottom. Let me show you how. So on the left, we have ball with coordinates 1, 0 and bat with coordinates 0, 1. And in the image embedding, ball has coordinates 0, 0, 1, 0 because, as I said, I'm reading these numbers like a page of letters, so 0, 0, 1, 0. And the bat has coordinates 1, 0, 0, 1 because I'm reading them from left to right, from top to bottom. And what I need is a neural network or a map that sends 1, 0 to 0, 0, 1, 0 and 0, 1 to 1, 0, 0, 1. And how do I build this neural network? Well, in the input, it's going to have 2 nodes because the embedding on the left has dimension 2, they're vectors of length 2. And because the embedding on the right has dimension 4 and the vectors have length 4, then I have 4 outputs, 1 for each of the 4 colors. And remember that the top right was blue, but I'm actually going to think of it as white because this one's going to be 0 all the time. So we really just care about the first, third, and fourth numbers. Now, I want 1, 0 to go to 0, 0, 1, 0. So I need this edge to be 1. Why do I need this edge to be 1? Because when I take ball, that is a 1, 0. And if I want this 1 to pass to the right, I multiply it by the value of the edge, which is 1, and I get a 1 here. And I have no edges elsewhere, they're all weight 0, so everything else becomes 0. And so the image of ball, which is 1, 0, becomes 0, 0, 1, 0, which is precisely the image of a ball in the embedding. As you can see, these numbers map to 0, 0, 1, 0. So this really simple neural network where I only have one edge maps the ball in the text embedding to the ball in the image embedding. Now let's do the same thing for bat. So what do I need for the bat in the left to go to a bat in the right? Well, if I take this edge to be 1 and this edge to be 1, then that works. Check it out. The coordinates for bat are 0, 1, so I put the 0, 1 here. And now, the 0 on the top becomes a 0 here, because it gets multiplied by the weight of the red edge. And the 1 on the bottom becomes 2 1s on the right, because it gets multiplied by the weight of the black and the green edges. And there's no edges going into the other node, so that node gets a 0. And so therefore, bat, which is the vector 0, 1, goes to the vector 1, 0, 0, 1. And that's precisely the image of a bat. And so this neural network does the job. And all I need now is to add zeros for all the other edges. And now I have my neural network that takes the ball in the text and sends it into the ball in the image, and the bat in the text and sends it into the bat in the image. And here's where some magic happens. There's no image of a ball and a bat anywhere. But in the text embedding, I have ball and bat as the vector 1, 1. Now what happens if I put the vector 1, 1 through this neural network? Well, 1, 1 is going to go to, there's a 1 going here multiplied by the weight of the red edge, which is 1. And the bottom 1 becomes these 2 1s multiplied by the weights of the black and green edges. And everything that goes to the other entry is a 0, is an edge with weight 0. So therefore this one has weight 0. And what did I get? Well, I got 1, 0, 1, 1, which is precisely the image of a ball and a bat. So this may look simple, but check out what happens. We train a neural network to draw a ball, and then we train the same neural network to draw a bat, and we never told it what a ball and a bat is. And from the image of the ball and the image of the bat, the neural network was able to draw the image of a ball and a bat. I know that looks simple, but that's where the magic lies. You can have a data set with certain images, and if you train a neural network well, it'll be able to combine these images into other images that are not in the data set. That, to me, is the key of Stable Diffusion. So this works well as an image generator. However, there's something I'm forgetting. What am I forgetting? Well, neural networks normally have a sigmoid function. This neural network we built over here was pretty linear, and that's not going to be the case all the time. So let's go back to reality and add a sigmoid function. What's a sigmoid function? Well, that appears on the neural network video that I've linked in the comments. But let me give you a quick refresher. The formula is this. Do not worry about the formula. I always like to think of a mental picture instead. So it's just a function that takes all the numbers, negative and positive, and sends them into the interval 0, 1. So here's the graph of the function. If you have a very large number, it sends it to something close to 1. If you have negative numbers, it sends them to something close to 0. If you have, for example, 1, it sends it to 0.73. You can calculate that in the formula. And if you have, for example, 0, it sends it to 0.5. So in other words, it takes the entire number line and shrinks it into the interval 0, 1. It's kind of like looking at the line through a lens. And why is it so useful? Because the outputs of neural networks are between 0 and 1. But out of these nodes, any number comes out. So you use the sigmoid function to shrink those numbers and put them into the 0 and 1 range. So we had our neural network here that outputs numbers. Let's not forget to put a sigmoid function at the end of each node. So what happens? Well, let's go back again. 1, 0 is going to go to 0, 0, 1, 0 because the ball goes to the image of a ball. Now, if I pass everything through a sigmoid function, I'm not going to get 0, 0, 1, 0. Unfortunately, I'm going to get 0.5, 0.5, 0.73, and 0.5. That gives me this image over here, which is kind of a ball but very fuzzy. You can sort of see the ball in the bottom left, but it's not so clear. What happens to a bat? Well, the vector 0, 1 now goes to the vector 1, 0, 0, 1. And when put through a sigmoid function, that becomes 0.73, 0.5, 0.5, and 0.73, which is this image where you can sort of see the bat, but it's not very clear. And finally, ball and bat will be 1, 1 that goes through 1, 0, 1, 1, that now goes to 0.73, 0.5, 0.73, 0.73, which is again a ball and a bat, but not super clear. In other words, we've managed to build a neural network that can draw a ball, a bat, and a ball and a bat, but unfortunately they're very fuzzy. So the question is, can we improve these images over here? Can we make them more crisp? Well, we can by making the neural network a little bit better. I'm going to improve it. Check this out. I'm going to turn those +1s into +2s. What's going to happen now? Well, ball, which is 1, 0, is now going to go to the vector 0, 0, 2, 0 because that 1 is going to be multiplied by 2, the weight of the red edge. However, 0, 0, 2, 0 is not that much better, but I can subtract 1 to everything here to get 1, 1 minus 1, 1. How? By throwing in a bias. The bias unit in a neural network is super important and it's pretty much a constant that you add to each of the nodes. So if my bias unit has edges with weight -1 going to all the nodes at the right, then I'm basically subtracting 1 from each of the values that we get at the end, and now we get -1, -1, 1, -1. Why is that good? Well, because now I'm spreading my values apart. The -1 becomes a 0.27 and the 1 becomes a 0.73, and we've managed to make the image just a little crisper. Now you can see the ball a little bit better. It's not as good as the previous neural network, it's better than the one that we just built. Now what happens with bat? Well, very similar. 0, 1 goes to, now it's going to be 1 minus 1 minus 1, 1, which becomes 0.73, 0.27, 0.27, and 0.73, which goes to this vector over here, which goes to the image over here. That is now just a little bit better bat. You can see it more in the diagonal. It's more clear than the previous one. Still not great, but much better. And finally, ball and bat. Well, that's a 1, 1 that goes to 1 minus 1, 1, 1. And that's a slightly better image of a ball and a bat. So we managed to make the images a little bit better, but they're still not perfect. So the question is, can we improve these even more? And the answer is yes, we can continue improving this neural network. And I'm going to show you a quick way, and I'd love for you to pause this video and actually think about it, make the calculations, and notice that if I take the edges and turn the weights into +100, and I take the edges coming from the bias unit and turn them into -50, then this neural network is going to actually give me crisp images of a ball, a bat, and a ball and a bat. But that's not what we want to do. I don't want to continue messing with this neural network because I don't want to assume that this neural network is going to do a perfect job. This neural network is very limited. It goes from text to images, and that's really hard. So in some way, I want to do something simpler that takes these images over here and says, you know what? This is good enough. You've done well enough, neural network. Don't worry. You've kind of managed to show me where the ball is and where the bat is and where the ball and the bat is. So you can go rest, neural network, because you've done a wonderful job. Now let me take it from here. In other words, the image generator gives us these images that are not that great, but that they capture the ball and the bat. And as long as they can capture it, that's good enough. Because what we're going to do is we're going to build a diffusion model that is going to improve these images. It's going to turn this rough looking ball and a bat and turn them into clear images of a ball and a bat and a ball and a bat. Actually, that's kind of optimistic. We may be able to get somewhere like here with 0.99s and 0.01s, but the diffusion model is going to clean the images up. And so next, I'm going to tell you how to build this diffusion model for this small example. Okay, so now it's time to build the diffusion model. Of all the ones we built today, this is going to be the more complicated one, but it's still not that complicated. So to remind you, we want to build a diffusion model that's going to take these rough looking images of balls and bats and turn them into nice sharp images. And in our very simple case, what it's going to do is it's going to take these rough looking pixelated images and turn them into their better version, where the light grays are turned into white and the dark grays are turned into black. And that's going to be the diffusion model. So first, I'm going to tell you how to train it if you were to train it. What you would do here is you would take a clean image, for example, a clean image of a bat. Then you would add some noise by adding or subtracting some random tiny numbers to it to get an image of a bat that is a little noisy. Then you would add a little more noise to this image. And then you would add a little more noise to the image until it's pretty much illegible what it is. And so you have a chain of images where you start with the crisp one and then you go noisier, 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 noisier until the end. And now what you're going to do is train a neural network to predict the previous one. So in other words, the input is the image with noise and the output is the image without noise for each one of the images. Now this is done for a bat. You also do it for the ball and for every image in the data set. So just like I showed you at the beginning of the video, you take lots and lots of images, you add noise to them, add noise to them, add more noise to them, and then you train the neural network to continuously be removing this noise at each step. And so then the neural network knows how to clean an image, and you may have to use it many times, but at the end of the day, you have a neural network that is trained to clean up an image. Now, in general, these are going to be very complicated, but for our simple example, it's actually going to be very easy. And the reason is because pixels here are not super correlated. In other words, what I'm going to do is basically clean up each pixel at a time. So if I have anything dark gray, so anything where the intensity is bigger than 0.5, I'm going to turn that into black. So any number bigger than 0.5, strictly bigger, I'm going to turn it into a 1. Any number less than 0.1, which is the lighter grays all the way to white, I'm going to turn into a 0 because that's the color for white. And let's say that if we have a pixel whose value is 0.5, we'll keep it as 0.5. That doesn't really matter for our examples. Now, I'm just doing this for this particular case and I'm taking an arbitrary construction. I encourage you to actually think of this and think of how would you build a diffusion model for this case. Maybe you have a better construction, a better architecture. And so how are we going to do this? So let's do some math. I'm going to take the dark grays and turn them into something much closer to black and the light grays and turn into something much closer to white. So I'm going to do some math with all these numbers. First, I'm going to center them because they're in the interval 0, 1. I'm going to put them into interval minus 0.5, 0.5, which means I'm going to subtract 0.5. When I subtract 0.5, now I get the numbers 0.5, 0.25, 0, minus 0.25, and minus 0.5. In other words, I centered them. Now I'm going to stretch this interval, so I'm going to multiply by 10. When I multiply by 10, now I get numbers between 5 and minus 5. So I get 5, 2.5, 0, minus 2.5, and minus 5. And now I'm going to apply sigmoid. So for high values, sigmoid goes close to 1. And for low values, negative values, sigmoid goes close to 0. So now I have numbers that are 1, 0.92, 0.5, 0.08, and 0. And that's going to be my neural network. So it takes 1 goes to 1, 0.75 goes to 0.92, so notice that it really cleaned up that pixel. It turned it from dark gray to pretty dark gray. It left the 0.5 the same, and then it took my light gray 0.25 and turned it into 0.08, which is a lot wider, and then the 0 left it at 0. And now I'm going to show you how to turn these operations into a pretty simple neural network. So let's look at one of them. Let's say the one with 0.75 that turns it into 0.92. What did we do here? Let's recall that first we subtracted 0.5, then we multiplied by 10, and then we applied sigmoid. Those are neural network operations. Let's organize them a little bit. So first, let's say when I multiply by 10, I have 0.75 times 10, and this minus 0.5, since it was done before multiplying by 10, I can actually turn it into subtracting 5, because 0.5 times 10 is 5. I'm just using the distributive property. So here I have subtract 5. And finally, I apply the sigmoid function. So this is the operation that I'm going to turn into a neural network. Let's start with my value of 0.75. The multiply by 10 means that I have an edge with a weight of 10. And now the output is 7.5. How do I subtract 5? Well, that's a bias unit over here, which is a 1, with an edge of weight minus 5. That's how I subtract 5. So now my output turns into 7.5 minus 5, which is 2.5. And finally, I'm going to apply sigmoid. So apply sigmoid to this 2.5, and I get 0.95. So that's a neural network. It's a pretty simple neural network, and I can do that for every single one of the 4 pixels. And I get this neural network over here, which I can clean up by putting the sigmoid inside the vertex. And that is my diffusion neural network. Now let's see how it works. For the image of a ball, it has this image over here, 0.27, 0.27, 0.73, 0.27. And as you've seen, that goes to 0.08, 0.08, 0.92, and 0.08, which is a much crisper image of that ball. The bat goes to this image over here, which is a much crisper image. And the ball and bat goes to this image over here, which is much crisper. Now, a small observation, which I already said, this is a very easy case because I cleaned up every pixel separately. Obviously, in a big data set with lots of images and lots of pixels, you're not going to clean every pixel separately. The neural network has to figure out correlations between pixels that correspond to the noise. So this can be a pretty complicated neural network, but you can think of it as a neural network that learns how to remove noise from images. And that's the diffusion model. And in the more complicated case, it's going to take images that are pretty fuzzy and turn them into much nicer and crisper images. And don't forget that this is a big neural network. So that's it. That is the diffusion model. So let me give you a little summary of what we saw today. The Stable Diffusion model for the example had a small data set of 2 words, ball and bat, and then it created the embedding for ball and bat. And this was a very small neural network. Notice that this one doesn't have the sigmoid function. It doesn't really matter. The embedding neural network for this case is so simple. But in the big case, imagine a full-fledged neural network that will take the words and turn them into embedding vectors. So this neural network outputted these vectors over here, 1, 0, 0, 1, and 1, 1 for the 3 sentences on the left. And then we needed another neural network to actually build the images. And this one built these kind of fuzzy images, where you can sort of see the ball and we sort of see the bat, but they're not super clear. But we then built a diffusion neural network that cleaned up these images and left us with some pretty nice images of a ball and a bat and a ball and a bat. These 3 are called the embedding neural network, the image generator, and the diffusion model. And in the big case, we're going to have a big data set with lots of sentences, and they're going to be turned into long vectors with a lot of numbers. Could be hundreds, could be thousands. And this is going to be done by the first neural network, the embedding neural network. Then the second neural network, the image generator, is going to turn these vectors into images that are not great looking. They're kind of fuzzy, but they're going to capture what's important. They're going to be able to draw that penguin in a slightly rough way, or the clown, etc. And then the diffusion model is going to turn that into crisp, nice looking images like the ones at the right. So all these 3 neural networks, the embedding, the image generator, and the diffusion model, are going to be the neural networks that form our stable diffusion model. And that is how images get generated. That's what you see in DALL-E, that's what you see in Dream Studio, and in pretty much any great image generator that you may be working with. Obviously, a full stable diffusion model will have a lot of little moving parts that make this work much better, but in high level, it's formed by these 3 big components. So that's all, folks. Thank you very much for sticking all the way to the end. I hope you enjoyed the video, and I hope you learned how stable diffusion models are. As usual, I couldn't have done this alone. I got a little help from my friends. In particular, my friend Suraj was the one who gave me the original idea. I was talking to him at a conference, and he gave me a big picture of how stable diffusion works, and that helped me build this video. If you like this, I want to recommend you LLM University. It's a course that we've built with my colleagues at Cohere, Mior Amer, and Jay Alamar, who are wonderful content creators. In particular, you should check out their material. Mior has some great books, and Jay has a wonderful blog and YouTube channel where actually he has a video on stable diffusion that you should check out. I used that video to learn a lot about the material I showed you today. So thank you very much. If you like this video, Please follow me on YouTube if you haven't. I put videos like this pretty often, and I try to always simplify concepts that are complicated using fun examples like you saw today. The channel is called Serrano Academy. Please hit like. Please comment. I love to read your comments and share it amongst your friends. You can also take a look at my page, Serrano Academy, serrano.academy, where I have a blog and I have all these videos and a bunch of other courses, etc. Or you can tweet at me. My Twitter is serrano.academy. And if you'd like to engage more, I actually have a book called Grokking Machine Learning. You can buy it on the link that I have in the description, and make sure you use this discount code SerranoYT. That is for a 40% discount. So thanks very much for your attention, and see you in the next video.